Tooling for a punch press consists of a punch, a die, and a stripper. The size of the punched hole is determined by the punch size, while the die size, or opening, affects the condition of the hole and tool life. The clearance between the punch and the die is based on the type and thickness of the material. The stripper is in contact with the workpiece during punching and until the punch is stripped or withdrawn from the workpiece. Multiple station operations are done with dies that have several stations. Each station simultaneously performs a single step in a series of operations needed to complete a part. Finished workpieces are discharged with each stroke. Multiple station operations can be performed using either progressive dies or transfer dies. In progressive die operations, parts are made from continuous coil stock and remain connected to the stock by a carrier strip during each successive operation until the final cutoff and discharge from the die. In transfer die operations, parts are blanked before or at the beginning of the sequential operations. Mechanical transfer devices grip and move the individual workpieces from die station to die station within a single die to complete a progression of operations. With large workpieces, a tandem press line may be utilized. Parts are transferred by gripping devices from press to press, instead of within a single die. Each press within the tandem line holds its own tooling and performs specific operations to form, trim, and pierce the part. Dies are the tooling that determine the shape produced on press brakes. The most common type of bending die is the 90-degree V-shaped die, but many other types are used to produce shapes, such as the acute angle die, the gooseneck die, the offset die, and the rotary bending die. Acute angle dies are usually used in air bending, where accuracy is not critical. Gooseneck dies essentially are V-bend dies, with clearance for return flanges. Since the neck of the die is usually out beyond center line, care must be taken to prevent overloading the die. Offset dies are typically used for long runs and require from 4 to 20 times more force for a single bend, depending on the nature of the offset. Rotary bending dies use a cylindrical rocker with an angular notch cut out along its length. As the punch descends, the rocker clamps the workpiece and bends it around a die anvil.
How do we go from this blank to this finished part?
During bending, an internal mandrel may be necessary to support the wall of the workpiece as it is pulled around the bending form. Mandrels are also used to reduce the amount of flattening in the bend and to help prevent wrinkles from forming on the inner wall of the bend. There are several different types of mandrels, including the plug mandrel, the form mandrel, the single ball mandrel, and the multi-ball mandrel. The tube is inserted over the mandrel and then positioned so that the mandrel is located in the region of the bend tangent. The mandrel is typically attached to a rod anchored at the rear of the bending machine. This rod has both lateral and longitudinal adjustment capability to position the mandrel properly for bending. During bending, the metal on the outside of the bend stretches across the formed tip of the mandrel, making it impractical, if not impossible, to remove the bent piece from the dies. Therefore, an extraction mechanism is used to remove the mandrel from the bend area.
All the parts we've made so far have been parts which can be taken directly from the mandrel. But what happens if we have a shape where once we've spun it we can't remove the shell from the mandrel because it has a waistline? Now, there's various ways that we can do this, but in this particular section and chapter I'm going to demonstrate plug tools or split tools. Now, if we take this hourglass shape, for instance, which is eventually going to be the base of a lamp, we can see that the diameter of the nose is much more than what this waist is, meaning that we wouldn't be able to remove it from the spinning tool. The same goes for this vase base here too. If we look at the mandrel and how it's been made, it can split into two sections, and then it gives you this nose or the plug at the end, hence the name plug tool or split tool. And what happens is the spinner will spin down the entire contour of the shape that it requires, like he has done here, and then cut the nose out and remove the shell, which we can do, but this plug will still be set inside the shell. This plug is then knocked out of the shell, leaving this shape. Now, this also on the end here, if you can see, has a rounded edge. Now, what's happened is it's been trimmed on the nose here, then it's been put back onto the mandrel, and this has been spun over with air spinning or spinning on air. But for the demonstration, let's concentrate on this lamp base, because the lamp base, if we look at the tooling, it's a much larger size and it's much easier to understand. Once the two parts are together, we get the outline of the actual shape that we need, but it has to be split at the narrowest diameter of the shell. So if we take this, and I'll set it up how it was before I took the nose out, I spun down all the way to the end. I then came around to the front and cut the nose out. That meant because there's a split right here in the tool, I can remove the shell and then simply knock out the nose.
Several drive arrangements are used on mechanical presses to transform the rotary motion of the drive motor through the crankshaft to the reciprocating motion of the slide. These arrangements include direct drive, single gear reduction, and double gear reduction presses. In non-geared or direct drive presses, the flywheel is mounted to the end of the crankshaft and driven by belts from the motor. Higher operating speeds are possible with this arrangement than with geared type drives. Other advantages of this simple design include fewer moving parts to wear out and less frictional loss of mechanical energy. Certain factors limit application of the direct drive, however. The full rated force of the machine is only available very close to the bottom of the stroke, and the ability to deliver rated forces is substantially reduced if the press operates at less than full speed. In single gear reduction presses, the flywheel is mounted on the back shaft and power is transmitted through a pinion to a main gear mounted on the crankshaft. A problem occurs with single end drive presses, however. Angular misalignment, proportional to the torque transmitted through a crankshaft with two throws, causes the side of the ram nearest the driven end of the crankshaft to reach bottom dead center before the other side. This results in a ram tipping alignment error. Angular misalignment of the crankshaft is avoided when the crankshaft is driven equally on both ends.